Hello, Aaliyah.
Hi.
How are you today?
Great.
Good.
No, I like videos.
So, got questions?
I mean, if I'm the only one, yeah, number 2.
Well, you're 5 minutes early, but you know, why waste
Wait.
time?
True. I forgot. I mean, that's my only question. Let's get it done.
Well, thank you, Bill. Or is it Bill Engvall? Nah, it's Larry the Cable Guy.
No, I don't know.
Splits his time between Florida and Lincoln.
Oh.
His name's like David something or other. I don't know. Okay, so let's look at the problem instead of talking about get her done. So a laser beam is incident on 2 slits with a separation of 0.012 millimeters. A screen is placed 4.8 meters away. Clearly the scale in this picture is not, a correct scale.
Yeah.
Hey, look, Anna's here. Hi, Anna.
Hi.
Maybe she doesn't have sound.
What?
Anna. Oh,
Okay.
we said hi to you. That's all.
Oh, hello. Yeah, I was saying with like computer audio, so I didn't hear that.
Okay.
We're working on
Are we
number
number
2.
2? Thank
Yeah.
God.
Okay, so we have the laser has a wavelength of 1,750 angstroms. Now, are you guys familiar with angstrom at all?
I've heard you say it before.
Yeah, that's about, yeah.
Okay. And actually, if we're going to pronounce it right, it's a Swedish A with a circle on top, and it should be pronounced ångström or ångström. You guys don't remember Åsa Karin? Can't remember Åsa's last name, but she was our registrar, and that was actually the first letter of her name, Åsa. Anyway, so that's equal to 10 to the minus 10th meters. So the first thing we have to know is just what that wavelength is in meters. Hi, Diana. No hablo español. Okay.
Sorry about that.
Okay, so we have our wavelength and we have the slit separation, and that's this θ1 and θ2 are the angles to the first and second bright fringes above the center line. So this one here is m equals 1 for θ1. This one's m equals 2 for θ2. And then we're asked to express sine theta in terms of d and lambda. Did you all get that first part, expressing sine theta in terms of d and lambda? That is our, for diffraction, for double slit diffraction or multiple slit diffraction, we have d sine theta equals m lambda for constructive, and d sine theta equals m plus 1/2 lambda for destructive. So when it says bright fringes, is that constructive or destructive?
Constructive.
Okay, so that means we're going to be using this equation. So there's the answer right there. For the first part, all you got to do is type in that equation, although it's sine theta is equal to. So if it's θ1, what is m?
1.
Okay, and so you're just going to have
Lambda.
m is 1, and you just divide both sides by d. And then for the next one, it is the same question except for it's θ2. So what's the difference here?
M is 2.
Right.
Wow.
Now down to part C. Actually, I got to say, express the distance between the 2 bright fringes on the screen in terms of θ1, θ2, L. So now we have to do some geometry work.
Oh.
So this position right here, if we take θ1, we have L is that side of a triangle, and Y1 is that side of the triangle. So what trig function would relate the known L with the unknown Y1?
Opposite over adjacent.
Okay, opposite over adjacent, which is
I don't remember.
tangent. So we have tangent theta 1 is equal to opposite side Y1 over adjacent L. And likewise, tangent theta 2 is equal to Y2 over L. We want Y2 minus Y1.
Why?
So how do we get Y2 minus Y1?
L tangent theta 2 minus L tangent theta 1.
Or to put it simpler,
L sine. Oh, that's where I gone.
that's just factoring out the L.
Then do you just plug in the numbers?
Yep.
My issue is
That's for C,
Yeah.
Yeah, that's for C.
but I don't. Okay.
issue is probably the converting here in part D.
Say that again, David.
My issue is probably the converting here in part D, like with the or whatever they are.
I still didn't understand you. The converging something.
Converting
Converting.
from everything else to meters.
Okay, so remember, angstroms 10 to the minus 10 meters. Millimeter, of course, is 10 to the minus 3 meters. And so you have, we all have different numbers, but you just need to put everything in meters and you should be good. Is it just me, or do they have crazy angles that are unrelated to the problem here? Alpha, beta, phi. Where did all those come from? But we only have theta 1 and theta 2. I don't know where all those other angles come from. But yeah, you just want to make sure your lambda, in my case, lambda was 1750 angstroms equals 1750 times 10 to the minus 10 meters. And my D was 0.0, was it 12? Yeah, 12. And there I have everything now into meters. So is everything working out here? Are you guys busy working, or because I'm
Trying to solve it now to see if it works.
okay. Hi, Isabel.
So we need to find theta first, right? Theta 2.
So yes, the first thing I would do is to actually calculate what theta 1 and theta 2 are from those two calculations.
I
And
did
then
this
plug
wrong.
those angles into here. Now, if you want to be lazy, none of us want to be lazy, right?
Mm-hmm.
I don't know how to do this.
The angles are probably small and you could use a small angle approximation. But I don't know what the angles are, and if they're not small and you use a small angle approximation, you'll be wrong. The small angle approximation is to say that sine theta is equal to tangent theta. And so you can, quickly do it that way. But if it's not a small angle, that's going to give you wrong answer. So it's a risk if you don't know what the angle is to try to do that.
I don't know how that.
Yeah, I'm like pretty confused.
How do you find from sine theta? Oh, never mind. I might know how to do this.
Okay, Anna, what do you need clarification on?
So after you like get the two like sine thetas ones, how do you like convert that to tan theta so that you can like?
Okay, so what you have the sine theta equation here, right? So you just put in here sine theta 1 is
Oh,
equal
because
to-
the sine theta equals tan theta. I forgot that part. Okay,
No,
never mind.
that's only for small angle approximation, which probably applies, but it's not technically correct. It's an approximation.
Right.
So you have sine theta is equal to lambda over d, right? That's what you have for your equation here.
Yeah.
And so if you look at the values for lambda and d, we can determine if this is a small angle or not by if this value is like less than 0.01, then it's a small angle.
So like my number was like for theta, lambda over d was 0.01369 one night. So is that small enough that I could use it?
It probably is. Just go ahead. Just go ahead and test, right? Make sure your calculator's in radians, and then do sine of that angle.
I did it in degrees and got the right answer.
Excuse me, David?
I did it in degrees and got the right answer.
Without using the small angle approximation, right?
Oh, yeah.
Yeah.
How do you find this?
Okay, that actually wasn't so bad.
So, Aaliyah, what was your question?
I don't know how to ask my question. I don't
Excellent.
know. I just don't even know where to start. Like, how do you find theta?
Okay, so
Works.
I will throw an extra page in here.
I'm so sorry.
No. Our goal is for you to understand. So we have sine theta 1 is equal to 1 times lambda over d.
Yeah.
And that means theta 1 is equal to arc sine, or sine minus 1 of 1 times lambda over d.
Okay, that's what I did, but I came up with like 0.9.
And is that radians or degrees?
I don't know.
Well, as long as you keep your calculator in the same mode, you'll be correct. Like David said, you did it in degrees. As long as you keep it in the same mode.
Oh wait, do you have to
Do I
do,
know what mode it's in?
is that a setting on your, yeah, I forgot about that. How do you change the setting?
What do you have, like a TIA degree?
Yeah.
Click mode on your calculator. It's like right here.
Oh, sweet. So
I'm
you
in
like
degrees.
change
Because I
it-
don't have a calculator.
do we have to change it to radians? Dr. Webb, is that what you're saying to do?
No, if you leave it in degrees, it'll work. If you leave it in radians, it'll work.
Oh,
And
So
only
the-
test if it's a small angle, you need to be in radians.
Is that a big?
No, it's not a big thing.
so actually like I was wrong. So my actual number is 0.784. I thought you said that it had to be like less than 0.1.
Yeah, you want to be, I like to be less than 0.01 just to make sure that there's no real error going to be introduced. So if it's
Okay, so
0.7
then we can't use that approximation then, right?
Right, so then you would want to just go ahead and calculate what theta is. So for instance, in my case, I had, my lambda was 1.750 times 10 to the minus 7 meters. And my d was 1.20 times 10 to the minus 5 meters. And so if I put that in the calculator, which I am going to do on a different web browser, maybe. So a sine.
Must it be our lambda times 10 to the negative 10?
Okay, so I got a value of 0.0145 radians because my Google gave me the answer in radians. Somebody just asked a question about the units, and so if I have 1.1750 times 10 to the minus 10, if I move it over 3 positions, that's 1.750 times 10 to the minus 7.
Or I can do, okay, yeah. So
And
it's
this
fine.
one here to the minus 3, I moved it 2 to the right, so that made it 10 to the minus 5.
Okay, so then what do you do when you have the theta?
Okay, so there's
2 and
theta 1.
Well, not theta, but like, well, yeah, because it is theta now, right? Because we took the sign out. So now can we plug it in?
Yes. Oh, this should have been sine, inverse sine. I forgot to put the inverse sine here.
Do we plug it in for the tan theta 2 and tan theta 1?
Yes. You plug in the theta 2 and you plug in the theta 1 into the equation.
Okay.
I'm probably going to get this wrong.
Yeah, I feel like I am too.
Is my final answer supposed to be tiny?
I don't know, David.
My answer was pretty small, yeah.
Like, I got 0.027.
I got 0.087.
Let's just see what happened. I was right. Oh my goodness.
Wonder of wonders. No wonder at all. You guys are smart people.
Oh, thanks. Okay, that actually was really easy. I don't know what's wrong with me.
Yeah.
Okay. And so then, I mean, you put that in calculator and you have your final answer for my numbers.
Yeah.
And something you might note is, indeed, the small angle approximation would have worked out fine here. If I hadn't done arc sine, if I just put the argument, I would have had the comparable number would have been 0.02916 repeating. So the error here would have been less than 0.01%. That's no problem if I'd used the small angle approximation. But you have to check and see first if it's applicable, not just go willy-nilly. I have seen textbooks that have answers in the back where they use the small angle approximation when the angle's 30 degrees. Not close to the right answer. Any other questions?
If we're ready to move on, let's do number 3.
All right. I want you to see Aaliyah's superiority look there because she's already done the rest of them.
Since she was bragging last night.
All right. So problem 3, passing an electric current through an unknown gas produces several distinct wavelengths of visible light. I don't think I ever got to do that with you guys, right? To have the little gas tube up there and you wear the cool little glasses and see the different colors. No, boo. It's totally fun. The polarization lab or lecture is like the most fun one I do every year. I didn't get to do that. Anyway, so it tells us that each one of these wavelengths are first order. First order maxima. So that means we're using the same equation as the last time. d sine theta 1 is equal to 1 lambda, well, that's it. So that's the equation we're using, and all we have to do is find what lambda is. Notice I can get rid of that parenthesis 1, right? Parenthesis 1 tells me nothing important. And so I'm just solving for lambda for each one of these. So we have only one real complicating factor. They didn't give us d. They gave us 10,000 lines per centimeter. So if I have a distance of 1 centimeter and I have n equals 10, that's never going to fit. I have n equals 10,000 lines there. Then what's the spacing between the lines?
1 over 10,000 centimeters?
1 centimeter over 10,000, that's correct. So you have to get that number. If you don't have that number, of course, all is lost. But once you have that number, it's just that number times sine of the angle they gave you.
Oh. Wow, that was...
And you do it 4 times. That's the difficulty. You have to do it 4 times.
Right.
Isabel, you shouldn't be so tired. It's like noon out there.
Oh, so I have to convert.
By the way, y'all noticed that Isabel is supporting Union College there with her shirt? Yeah. Any questions? Anyone have a question?
When or where are the signups for the test?
For the test, I haven't put it up yet. It'll be a, you'll get a Google Calendar invitation that, it was kind of weird. Like everybody gets the same invitation. It has all the time slots. And then you accept it and it takes you to another page where you select the time slot you want. I did it for another class where I have a test immediately following our meeting here. But I haven't sent it out to you yet.
Okay.
We still have to do scrapbooks.
Yeah, you still need to do the scrapbooks.
Okay.
Any other homework questions here or questions about physics or what we're talking about in class, the lectures?
I just have like a quick question about the lab.
Uh-huh.
So like, I'm pretty sure that a lot of the lab, like, I did wrong, but we like tried really hard and we worked on it like all of lab time yesterday. So like Sarah, Lee, and I like worked on it together. Like we obviously didn't like have the same answers, but we like worked on it together. Like we were in lab and we worked on it basically the whole time we were in lab and we were struggling. And I don't think that we like got consistent answers throughout. So like as long as we tried and we like say our reasoning, we shouldn't get counted off for it, right?
Well, it depends on, you know, it depends on what kind of error there is. Let's look at it real quick. Real quick being, of course, relative terms. In college course management. I'm not logged in.
I don't know, just like one of the questions was like, was your answers consistent? And like we found that our answers were not consistent. So
I just don't know
that
if they
was
were
what was-
supposed to be.
Yeah, I don't know if it was supposed to be consistent, but like ours were not.
Okay, so I am going to change my sharing so you can, assuming I get logging in, you can see my screen instead of seeing just. So find the lab, we have two things. We have instructions. Well, great. I'm just going to download it anyway. It's the quickest way to find it. And please, hopefully. Okay, so going to our instructions. Nope. I've got to open the instructions apparently separately. Downloads. Okay, so here's our instructions. So, you know, this first one, try to recreate the picture shown on page 1 with the simulation using interference simulation for 1 and 2 and slit simulation. Use the laser option for the light source to try to do them. So first I'm going to have a single light source, and that's actually the really obvious one. So we use the interference option for the first 2, turn it to the laser option, only turn on 1 laser, and I can put it at the center. And I told you to turn on the screen, and I actually like to run the intensity so I can see it. And now that looks pretty similar, but it's very uniform. So I'm going to just try changing. Oh, and the color. I can move the picture. The color is supposed to be yellow. Kind of yellow. And so I'm going to look at this and say, does that look like what's in the picture? And yeah. It doesn't exactly, does it? When I did it before, I thought it looked the same, but now it doesn't. Well, what am I going to do? So, you know, that's how I simulated the first one. I just, to make it toward the center, I made the separation as small as it would go. I made sure that my color was the right color, and that was it. Then for the second one, I have 2 lights, and I want it to be dark, 2 dark spots, and then bright at the edges. So, long thing. But now I need to have both of them, and I want to have, I still don't like my color yellow, but I can't control the slider very well. There. So I wait for it to build the pattern, and right now it just has one center. Clearly not sufficient, so put them farther apart. And now they're too far apart, so you just have to adjust the spacing to get that. I know I'm going through the whole thing here. Where did you actually feel like you ran into difficulty?
Let me just like the only, I don't know, I think we did the rest of it right, but like for on page
2F.
yeah, something F.
The one we talked about?
No, it was, okay, so in part 1, not letter, I think it's C and D, it's saying what happens when you move the slits further apart or closer together.
Mhm.
And we had decided that, I'm trying to remember, that if you move it closer, there's more like black lines on the screen.
Well, what you're looking at is the screen here. Can you see where my pointer? No, you can't see where my pointer is. You're looking at the screen right next to the graph.
Yeah,
That's all you're looking at, right?
yeah.
Okay. And so here, they're as close as you can get.
Wait, use it with the slits if you can, because that's what it was.
Well, one of them is with the lights and one of them is with the slits.
Okay.
So with the lights, as close as I can have them together, I basically only see the central peak. If I move them far apart, then I'm going to see lots and lots of peaks. And so the separations get closer together when I move them farther apart. Then for the slits, so I have to go, whoops.
It did that to me too.
Yeah, I hate that. I'm going to copy this so I can just paste it next time. So going to the slits, and it's double slit, so can get the 2 slits. Turn on the light.
So I think that our main thing was that like for on page 5, part E, we were saying that like when the D is increased, the interference pattern is destructive. And then like when D is decreased, the interference pattern will be constructive. But then I think that for like some of our other tests, it was like opposite. So I don't know. I think that was like the main one, like
Okay, so
the
which
main
one then?
problem that we had.
Scroll down to section 2, the last one, I think.
I
of
did
it, the
you-
last
oh.
letter.
Section 2, the last letter.
I think. F. Yeah, it says, are they consistent? Are they supposed to be consistent? Because I didn't get mine to be consistent.
Yeah, that's what we all got. Like we didn't get that our things were consistent.
Okay, so
Which I think they should have been.
Yeah,
They-
that's
they
why we
should've-
think we did it wrong.
they should have been because 1C, or excuse me, 1D, when the slits are brought closer, farther apart. And then we were down here to,
So for D, we said that when the slits are closer together, there are fewer dark bands seen on the screen, and when they are further apart, there are more dark bands. And then for like page 5, number E, we were basically saying like the opposite was happening, that like when D is increased, the interference pattern is destructive, and when D is decreased, the interference pattern is constructive, which I think is the opposite of what we were saying earlier. That's why we're like, well,
this isn't going to be constructive versus destructive.
Then what is it meaning by interference pattern?
yeah, like
Okay.
why wouldn't it be
So the interference pattern is looking at this pattern. And so it's basically E is answering the same thing as you answered in 1D. What happens to the interference pattern if D is increased? Well, that's what you did in 1D. In 1D, you said, what happens to the pattern when the slits are brought closer and farther apart? D is the spacing between the slits.
Yeah, so in part E, I said that if you increased D, so made it further apart, you would have more like bright spots, so less dark bands.
So why is this actually showing one slit instead of two?
So part D, we said that when the slits are closer together, there are fewer dark bands,
Which is opposite of what we
which
said.
is what we just said for E.
So here the slits are close together, and so we have, with them relatively close, we have a total of 1, 2, 3, 4 dark bands. And then if we put them far apart, you have lots and lots of dark bands. And so when they're far apart, you have a lot more dark bands. When they're
Yeah,
closer
that's what we
together-
said for D. So then is our E wrong then?
Yes, because E is asking the same question.
Okay, so what's our reasoning behind why E is like that then, based on the equation?
Okay. So the reason you have these two questions is because E is asking you to use, this is using the small angle approximation equation. And so E is asking you, say, if D decreases, then theta must increase according to this equation. So it's
But what does
asking
that
the
have-
answer based on that equation for E. And the answer is, it better be the same because it's the same situation. It's just one is looking at the equation, one is looking at the actual simulation.
So
But what does that have to do with like the interference pattern?
The interference pattern is what we see in this screen. I know you can't see that I'm pointing to it, but what we see in the screen
So when
at the end.
that makes sense, I guess. Yeah, it does. Okay.
And the reason I have the graph on here is because the graph shows you when you have constructive interference, it's going out to the right. When you have destructive interference, it's right on the left. And so you can see where you have constructive and destructive interference looking at the graph.
Once we're done with the lab stuff, can we go to question number 5 on the homework?
I have to, you're good to go there, you said, Aaliyah?
I said, yeah, you can go to.
Okay. So number 5. Now, number 5, if you go to this website, it actually gives you some good information about the single slit. So I have it open here. At least I did have it open. And so if you, or not a single slit, but a circular aperture. So with that circular aperture, your geometry is a little different, so your equations come out differently. But what you have is a minimum when M is not an integer now, but 1.220. And then another one at 2.233, another one at 3.238, and a maximum of 1.635, and so on. And so you get an interesting interference pattern. Now, the question is asking about Rayleigh's criterion for differentiating two things, which is what you were actually using for the last part of the lab. So Rayleigh's criterion is when first from one object overlaps with center from the other, we can resolve. So basically that's saying that, well, the first minimum occurs at sine, that's a S, sine theta equals 1.22 lambda over the diameter of your aperture. And once again, just to make sure that we have,
1.22.
what was that?
There, right
The
there.
1.22 comes from right here, which you can't see me circling, but I was. Actually, I can annotate, now you can see me circling, it comes from right there. Right, so it's combining this equation with that number for the first minimum.
Okay, what about this, this y equals capital D, the format, the equation
Okay,
below?
so this is using the small angle approximation and the tangent theta like we did in problem 2.
Yeah.
Okay, go back. Oh, I gotta turn off annotate. Yeah. Hey, look, the annotation stayed over. I'm sure there's a way to get rid of those, but for now, scroll like that. Okay, so given that we have the pupil of the eye is 2.5 millimeters in diameter, so that's the D that we use in this equation, which you notice I used a capital D, that's what they use for, capital D. And the distance from the paper to the eye is 31 centimeters. And so what we're gonna have is based on our numbers, this is lowercase, or no. I've got to get my, I've got to get my numbers straight. We have the diameter of the eye is capital D. We have distance from the paper to the eye is 31 centimeters. Find the minimum separation. So we're looking for this X between two dots such that they cannot be resolved.
Okay, so basically we want to find the angle from the eye. So we want to find theta and then do simple trigonometry to find x, right?
We have two trig things. Well, one trig, I guess, you're right. We have tangent theta is x over 31 centimeters, and we have sine of theta is equal to 1.22 lambda over the diameter of the pupil.
Okay.
And as you saw, they used the small angle approximation. They said tangent theta is equal to sine theta is equal to theta. That would be true if 1.22 times my wavelength is much less than the diameter of the eye. So that'd be 1.22 times 555 nanometers divided by 2.5 millimeters. Well, if you multiply that through, which of course I just use a web browser to do, 1.22 times 555 e minus 9 divided by 0.0025. With my numbers, that gives me equals 0.0002708 Clearly, that's a small angle, right? And so that means I am now in a regime where I can set tangent theta equals sine theta. And I can just solve. There's got to be a way for me to clear all drawings. There we go. And so I'm just going to say x over 31 centimeters equals 1.22 lambda over d over 2.5 millimeters. And now I have 3 units, centimeters, millimeters, and nanometers, but it's just math.
Okay. Will on the exam, if we talk about that on our equation sheet, we'll be given those the minima and maxima M numbers, or is that something we need to remember?
You will have the equation for minima and the equation for maxima, I believe. Is that what you're asking?
Not the equation, like the 1.22. Will we have that list, or the number that we'll need to memorize?
No,
It's on
you're
the
going to have the equation. You don't have to memorize it.
Okay.
Yes?